The 22nd of December, 2022. Winter storm Elliott was tearing across the United States, with temperatures dropping to record lows in cities that rarely saw snow. Every major American airline canceled hundreds of flights. American Airlines canceled 1,450. United canceled 918. Delta canceled 1,200. Each of these carriers grounded aircraft, apologized to passengers, and issued rebooking instructions. And then, over the following 48 hours, they recovered. Their systems stabilized. Their crews repositioned. Their schedules restabilized. Southwest Airlines canceled 16,700 flights over the following 10 days. More than 2 million passengers were stranded. Crews were sleeping in airports because the airline's scheduling software could not tell them where they were supposed to go next. Baggage went missing. Customer service lines went unanswered for hours. And while every other American carrier was back to near normal operations, by Christmas Eve, Southwest was still canceling the majority of its flights on the 28th of December. An airline that had spent 5 decades building a reputation for operational resilience. An airline that had famously been the most profitable in American aviation history collapsed. The question that the DOT investigation, the congressional hearings, and the airline's own internal review all eventually asked was the same. How did a storm that every other airline survived destroy Southwest entirely? To understand the collapse, you have to understand why Southwest was different, and why that difference, which had been a competitive advantage for 30 years, became a catastrophic liability in 72 hours. Every major American airline, Delta, United, American, operates a hub-and-spoke network. This means that the overwhelming majority of flights connect through a handful of major airports. Delta's hub is Atlanta. United's hubs are Chicago O'Hare, Houston, and Newark. American's primary hubs are Dallas, Fort Worth, and Charlotte. In a hub-and-spoke model, when a storm hits a hub, you cancel the flights into and out of that hub. Your aircraft and your crews are mostly located at hubs, which means recovery is geographically concentrated. You move aircraft back to hubs, you reposition crews through hubs, and the system restabilizes because all the pieces are, by design, supposed to be in a small number of places. Southwest does not operate a hub and spoke network. Southwest operates a point-to-point network. Every Southwest aircraft flies a sequence of city pairs throughout the day. Dallas to Denver, Denver to Phoenix, Phoenix to Chicago, Chicago to Baltimore, without routing through a hub. This model generates several advantages. It eliminates the connection fees that hub airports charge. It enables more direct routing that saves passengers time. And it generates much higher aircraft utilization because planes are never sitting at a hub waiting for connecting traffic. In good conditions, point-to-point is a genuinely more efficient model than hub-and-spoke for a carrier of Southwest size and route network. But the point-to-point model has a specific vulnerability that hub-and-spoke does not. When things go wrong, the recovery problem is not concentrated. It is distributed across every airport in the system simultaneously. When Elliott hit in late December 2022, Southwest's operations began degrading in the affected regions, primarily Denver and Chicago, where temperature extremes were causing aircraft mechanical issues and crew scheduling problems. At a hub airline, this would mean disruptions at those hubs. At Southwest, it meant disruptions across every downstream city that those aircraft and those crews were supposed to serve that day. An aircraft that was supposed to fly Denver to Phoenix, then Phoenix to Houston, then Houston to New Orleans, didn't make the Denver to Phoenix leg, which meant it wasn't in Phoenix, which meant the Phoenix to Houston flight didn't operate, which meant the Houston to New Orleans flight didn't operate. Each cancellation cascaded into 3 or 4 more, because Southwest's schedule had assumed continuous aircraft utilization in a chain. By itself, this cascade was manageable. What made it unmanageable was the second layer of the problem: crew tracking. Airlines in the United States have strict FAA regulations governing crew rest, duty, time limits, and the maximum number of hours a crew member can work within any given period. Tracking which crew members are legal to fly, which flights, given their duty history, rest locations, and current position, is a computationally complex problem, even in normal operations. At Southwest, this tracking was managed by scheduling software called SkySolver, a system that had been developed in the 1990s and had been incrementally updated, but never fundamentally redesigned. When storm cancellations began disrupting the normal pattern of crew movements. Skysalver struggled to process the volume and complexity of real-time changes. Crew members were not where the system expected them to be. The system could not efficiently calculate legal reassignments. It began producing outputs that were delayed, incomplete, or inconsistent. The result was that Southwest's Operational Control Center, the team responsible for coordinating crew assignments across the network, lost the ability to accurately track where its crews were. Not approximately, precisely. Crew members were calling the airline's phone line to report their locations because the digital system could not tell anyone where they were. This is the moment the collapse became total. Cancellations that were triggering recoverable operational disruptions crossed into unrecoverable territory. To recover a disrupted airline schedule, you need to know where your aircraft are, where your crews are, and which crew members are legally qualified to operate which aircraft from which locations. Southwest knew where its aircraft were. It had GPS and maintenance tracking, but it did not know where its crews were with sufficient accuracy or speed to reassign them. So it couldn't reassign them. So it kept canceling flights, not because the weather was still severe, not because the aircraft were broken, but because it could not match available crews to available aircraft quickly enough to operate the schedule. At its peak, Southwest was canceling more than 2,500 flights per Dalton Y. The airline had enough aircraft. It had enough crews. They were just not in the right places, and the system could not tell anyone how to move them. The recovery, when it finally came, required Southwest to essentially rebuild its schedule from scratch over several days, manually repositioning aircraft, manually clearing crew assignments, manually rebuilding the sequence of operations that Skysalver was supposed to manage automatically. The process took until the 30th of December before cancellations fell below 10% of scheduled operations. The financial and reputational cost was enormous. Southwest estimated the total impact at approximately $800 million, including $300 million in refunds and reimbursements to affected passengers, and the rest in lost revenue from canceled flights and reputational damage to bookings. In the following weeks, the Department of Transportation ultimately fined the airline $140 million, the largest penalty ever imposed on a U.S. airline, for failing to provide adequate customer service. The fine included a requirement to compensate future passengers who experienced significant delays or cancellations. The congressional hearings that followed produced genuine accountability. Southwest CEO Bob Jordan acknowledged that the airline's operational technology had not kept pace with its operational complexity. The specific admission that Skysalver was not designed for the scale of recovery required by a system-wide disruption was striking because the problem had been known inside the company for years. Southwest employees and union representatives had raised concerns about the scheduling system's limitations before the meltdown. The airline had been planning upgrades. They were simply not complete when the storm arrived. The lesson of December 2022 is not that hub and spoke is better than point-to-point. Delta's hub and spoke model has its own vulnerabilities. The lesson is that Southwest had built its competitive advantage, tight scheduling, high utilization, point-to-point flexibility, on a technological infrastructure that was never designed to fail gracefully. When the failure came, the model's greatest strength, the distributed, interconnected nature of its network, became the mechanism of its collapse. The financial reckoning was immediate and substantial. Southwest recorded a pre-tax loss of approximately $800 million, directly attributable to the December meltdown, a combination of refunded fares, hotel and transportation reimbursements, compensation payments, and the revenue simply lost from the more than 2 million passengers who did not travel on Southwest during the disruption period. The Department of Transportation fined Southwest $140 million, the largest airline penalty in American aviation history at the time, citing failures to adequately assist stranded passengers and delayed refund processing. The reputational damage, harder to quantify, manifested in booking data for the following quarter. Southwest's bookings underperformed industry trends for several months after the incident, as passengers who had previously defaulted to Southwest began considering alternatives. The crew positioning problem specifically deserves examination because it reveals how deeply the structural vulnerability had developed. Southwest's network, at its operational peak in December 2022, had more than 16,000 active crew members, managing schedules across 121 airports. Unlike hub and spoke carriers where crews typically end their days back at a main hub, making repositioning after disruption straightforward. Southwest's crews end their days wherever the last flight of their trip takes them. On a normal day, SkySolver tracks all of this and re-optimizes continuously. When SkySolver was overwhelmed, crew schedulers were left trying to manually reconstruct the positions of thousands of crew members across 121 airports, using spreadsheets and phone calls, in the middle of the worst winter storm in years, while the phone lines were flooded with stranded passengers. It was not a failure of effort, it was a failure of architecture. A system that had been built to run the network at normal speed had no degraded mode fallback when normal speed was no longer possible. The specific upgrades that Southwest had planned for SkySolver, and that were not complete when Elliott arrived, involved improved crew positioning algorithms and better integration between the crew scheduling module and the real-time disruption management system. Southwest had been aware that its scheduling technology was a liability. An internal technology assessment conducted in 2019 had flagged the need for investment. COVID-19 interrupted and delayed the technology overhaul that the 2019 assessment had recommended. By December 2022, the technology program was in progress, but not deployed. The window between knowing a system is insufficient and replacing it with something better is the most dangerous period in any critical infrastructure. Southwest was in that window when the storm arrived. Southwest did not break in December 2022 because of a storm. Storms happen every winter, and Southwest had survived them for 50 years. Southwest broke because the system that was supposed to manage disruption at the speed and scale its network required had not been rebuilt to match the airline it had become. The meltdown was not a weather event. It was a technology failure that had been years in the making, waiting for a storm that was finally bad enough to expose it.